Let's look at a particular ocean instead of this zonally mean, zonally averaged meridional section that we looked at. As I said, because the ocean has boundaries, it really doesn't make that much sense to look at the ocean as a zonal mean meridional, which makes much more sense for the atmosphere because it's circumglobal, right? So here it is for this section through the Atlantic, kind of following the middle of the basin as it moves around. And this is the temperature. This is called the hydrographic section. So basically when the ships go around and measure temperature and salinity using various instruments like XBTs or CTDs and other things. XBTs only measure temperature, but nonetheless. CTDs are conductivity, temperature, and depth profiling instrument, which is lowered from the deck of a ship. Conductivity measures salinity, temperature, and then depth measures pressure, of course, right? So those sections called hydrographic sections, looking in the middle of the Atlantic, going from its southern end to its northern end to the bottom of Greenland, for example. You can see that the structure we have looked at before in the zonal mean is still there, with a subtropical gyre here and the subtropical gyre here, which is asymmetric. They are not exactly the same, and you can see the deep ocean getting fairly uniform as you go down. But when you look at the temperature structure, you can begin to see the penetration of these heavier salinities down into the region here, and you see some cross-equatorial structures as well, both near the surface and in the deeper ocean, right? That's not so obvious in the temperature, even though these profiles look like what we had seen before. So you can see that maybe some water is coming in here, some other water mass is going in there, and so on. So we will see that these are the density driven or so-called thermohaline circulations. Okay, that just gives you a good sense of how ocean circulation is different. The ocean, another big difference compared to the atmosphere is that it is forced from the top. The heating, the cooling, the wind forcing is all happening at the top, and wind forcing is entirely dependent on friction. It's the friction between the winds and the ocean surface that's able to put the energy into the ocean and create currents, right? So we have to look at the surface mix layer in the ocean. Unlike the atmospheric circulation, we did a lot of things, but we never mentioned the frictional boundary layer. It is very important, of course, but in this particular methodology of building up the equations to the general circulation and the large-scale balances, we didn't actually get into the planetary boundary layer. But in the ocean, it's impossible to do that because all the forcings are coming from the top through this surface boundary layer. So there is radiative heating and cooling happening. Okay, you can see cooling and heating, and there is heat loss and evaporation, and there is wind forcing, right? So this can be collected into what is called turbulent kinetic energy. So that's the energy that the atmosphere is constantly putting into the ocean. What happens at the ocean surface then? You end up mixing and creating a turbulent mixed layer, often just called mixed layer, but some people call it surface mix layer because you can also have a mix layer at the bottom because of friction, right? Nonetheless, the mix layer is fairly uniformly mixed in terms of temperature vertically, and then there is this sharp gradient that we mentioned as the thermocline. Thermocline means temperature gradient. You will get a similar thing for salinity and density, but the other way nonetheless. You have convection happening in the surface, as I mentioned before. The heating and the cooling can create heavier water, especially in winter months, for example, and they can sink down to the thermocline. It takes much more energy to penetrate the thermocline and go deeper, so the energy required to mix across here depends on how sharp this gradient is. It's literally like a jump at the bottom of the mix layer. Okay, so this turbulent kinetic energy determines how much of the cold thermocline water is entrained into this surface mix layer. So this term shown here as entrainment is a critical process. Okay, so you can think of the upwelling that we mentioned before. Upwelling lifts the cold water up towards the surface, okay, and it can make the mixing much more difficult. But if you have turbulent kinetic energy available from cooling and winds and so on, then you can entrain that cold upwelled water into the surface. This turns out to be very critical for the eastern Pacific, where we saw that the temperature, sea surface temperature, was much colder than the western Pacific. The western Pacific is around 29 degrees centigrade, whereas the eastern Pacific can be 22, 23 degrees centigrade. So this huge gradient is created by the wind-driven upwelling and then the turbulent kinetic energy entraining that upwelled cold water into the surface. Turns out to be very critical for the heat budget, for biological production, for exchanges of various gases like CO2 and so on. I will show another image of mixed layer depths, but this is a map based on some hydrographic data that's been collected over many years. So this is just a climatology, which means it's a long-term average distribution of mixed layer depths for the boreal winter months and the boreal summer months. And intuitively you can imagine why mixed layer is deeper in the winter, because there is heavy cooling at high latitudes, and that cooling creates heavier water which convects down and creates a turbulent mixed layer that's deeper. Okay, deeper means what? This range is basically from 100 meters to here it's 1,000 meters, but you have to be careful in this case because the wind currents can be still trapped to a very shallow depth, whereas the density surface can be much deeper. Details that we won't get into necessarily. Nonetheless, you can see that when the summer comes and the heating happens, the entire water column gets stabilized, which means the temperature is warm and this gradients get stronger, so the turbulent kinetic energy is not able to mix down as much, so the mixed layer depths shallow, they shoal, and you will see that these are now in the range of less than 100 meters. And during the boreal summer, obviously you have winter in the southern hemisphere and you get cooling and much deeper mixed layers at higher latitudes in the southern hemisphere. And you can see that much of the ocean here remains in the range of 30 to 100 meters, and the seasonal change is not large, but that's only in this kind of large scale map. We'll get into the specifics of particular regions, let's say of the tropical Pacific, and you'll see that there are changes. Even if it's between 20 meters and 50 meters, it can still make a big difference in terms of the heat content change, and that matters for the atmosphere. Remember that the atmosphere cares about how warm the ocean is, and how warm the ocean is depends on where the energy is getting trapped or how deep the mixed layer is. Okay, so all these things are related. So in the ocean, these are very critical. So in the atmosphere, we saw large scale surface pressure variations, low in the deep tropics, high in the subtropical gyres and the subpolar lows. We had seen the zonal winds and the meridional winds happening, and we had written the equations for buoyancy frequency as well. I'm not going to spend too much time explaining this again. We know exactly how we did this. For the ocean, for the atmosphere, we had written n squared, the buoyancy frequency, in terms of temperature. I have a chopper coming, so it's going to spoil this, so I'm going to just stop for a second. Just look at me as the chopper goes by. So the main message is that the equations of motion we had written before can be simplified by using our rho ref. So we can see that the equations became simpler by assuming that rho is not as variable in the ocean as in the atmosphere. If we take these equations we had derived for the whole system without saying whether it was compressible fluid or incompressible fluid. So we will see how these equations become simpler. Okay, so the surface mixed layer here is directly forced in the ocean. I'll come back to the equations again, okay, don't worry. But the thermocline here is not directly seeing the atmosphere except in a few places where the mixed layer can almost disappear. Okay, there are such places. So the thermocline is indirectly forced by the surface properties getting injected into the thermocline at special places where the boundary conditions are able to reach the thermocline directly. And once the properties go deep into the ocean below the mixed layer, they can hide there for a longer time because the thermocline doesn't communicate directly with the atmosphere too much. Okay, so that's the big difference in the ocean and the atmosphere. The mixed layer, the frictional boundary layer in the ocean, is very critical, so we have to start with that as opposed to the atmosphere where we did not mention it at all.